Hello there, welcome back to Algebra. So I want to just start this lesson by reviewing some things that we may not have reviewed, we may not have covered in enough depth in the previous lessons, and it is definitely worth repeating and having a quick recap of those things. So specifically, I want to talk about the difference between evaluate, simplify, and solve. These are things that are going to be expected of you in every math class you take from here on out. So let's just get into detail with each of these things and see exactly what we're supposed to do. So what does it mean to evaluate? Well, the word evaluate, it kind of has the word value in it. We always want to look for root words when we are investigating new vocabulary words. I can't type and talk at the same time, apparently. I have to type this first, evaluate. So it has the word value right there in it. So to evaluate something is to assign it a value. So in an algebra context, specifically, it's when we have something like this. Oops, I meant to make that an x. What if we have, for example, x squared minus 3? So what if we wanted to evaluate when x is 4? So to evaluate, to assign a value, is to replace this x with the value that we know it is. So instead of x squared minus 3, we're going to have 4 squared minus 3, which gets us 16 minus 3. So we have a grand total of 13. So we've successfully evaluated it at the value x is 4. We've assigned it a value. Now let's talk about what it means to simplify. So simplifying is something that we've had a lot of exposure to much, much earlier than these other concepts. So there are many, many different things we can simplify. We can simplify a number expression, combining them into just one term. We can simplify a fraction by making a common denominator. We can maybe, I don't know how I was going with that. We can simplify a fraction by reducing it. So to simplify just means making things a bit less complicated, because the less complicated things are in math, the easier it is to find the solution, and the easier it is to communicate that solution to other people, to explain your work, explain the steps you use to get your answer. So this is one heavily used example of simplification of an expression or an equation. We can also do something like this. We could say we have, like, I don't know, maybe 5x minus 3 plus x. And then we can combine like terms together. We would get 6x minus 3. That's just a quick explanation of what simplifying means. And then the last thing we have is solve. And I think this is the most important out of the three. So solving, whenever you're asked to solve something, you are given an equation. You can't solve something without an equation. You can only solve things that are in the form of an equation. So for example, what if we have 4 equals 3 minus x? We have an equal sign we're being asked to solve. Yip. Yay. So what does it mean to solve something? What does it mean to solve for a variable? Well, x is a container. It contains a hidden number. We don't know what it is, but let's see if we can find it. Let's see if we can find the value of x that makes this true. What if x is 0? If x is 0, we get 3 minus 0, which is not equal to 4. So that's not a very good number to use. So we can actually be a bit more strategic in how we go about this one. We're solving for x, which means we have to get rid of all of the junk surrounding x. So we're going to start by getting rid of the 3. We're going to subtract a 3 on both sides. We get 1 equals 0 minus x. So basically, it's just negative x. And if we multiply both sides by -1, we're going to get the solution. The solution is what we call the answer to a problem that we just solved. So we were given this equation. We're asked to solve the equation. Our solution is x is -1. If we plug in x is -1 into this expression, into this equation, it would be a true statement. If we plug in anything else but -1, it would be a false statement. So that's what it means to simplify. We're just finding a value that makes an equation true. So in this video, we're going to dive a bit deeper into the concept of a quadratic, what they are, what they look like, and the various operations we can do on them to make it easier to solve complex problems. But before we even do that, let's do a few more concrete examples of evaluate, and that would kind of segue us into the next topic of discussion for the night. So let's say we have 3x equals 0. And I apologize, this isn't evaluate, this is actually solve. So we're going to divide both sides by 3. So we get x is equal to 0. And that's a property that's specific to any kind of situation of this form. Whenever we have something times something equals 0, the x is going to have to be 0 because anything times 0 is 0. So x can't be anything but 0 in that case. That's called the zero product property, and that's worth writing down. So it's the zero product property that tells us if we have a bunch of things being multiplied together, a bunch of factors, the whole thing would end up having a value of 0 if just one of those things happens to be a 0. So let's say we have a times b times c times d times e times f equals 0. So what if b is 0? So if b is 0, we have this entire thing is equal to 0. Same thing would apply if a is 0 or c or d or e or f. If at least one of these things is equal to 0, the whole thing is going to go to 0. And that's the zero product property. The product of something and 0 will always be 0. So this brings me neatly into the next thing I really want to discuss. I'd really like to get deeper into the concept of quadratics, how to solve them, how to graph them, how to do, like I said a few minutes ago, all these various operations we can do on quadratics. So let's remind ourselves what a quadratic really is. A quadratic has a degree of 2, and a degree is just the highest exponent present on a variable in an expression. So for example, what if we have something like this, x cubed plus x minus 5? The highest exponent is a 3, which means that this is the third degree polynomial, and it is not a quadratic. For it to be a quadratic, it has to be a second degree polynomial. If it has a degree other than 2, it is definitely not a quadratic. So we have our quadratic right here, and a really common thing that you're going to be asked to do constantly throughout math is to set something like this equal to 0 and then solve. So we have a lot of really cool strategies we use to solve quadratic equations like this. It's not so simple like linear equations. What if, for example, we didn't have the x squared? What if we just had this? We'd be done in 5 seconds. Add 5 to both sides and bam, we're done. But unfortunately for us, things work a bit trickier with quadratics. Not so easy to work with. We have very, very specialized methods we've used that have been tried and true. I can't talk this evening, that have been tested and verified over the years that these things actually work really well and efficiently. Excuse me. Get some water. All right. So this is a quadratic because it has a degree of 2. What's another way we could express a quadratic? Let's say we have 2 binomials multiplied together, x plus 1 times x plus 2. Believe it or not, this is actually a quadratic. You might be thinking, oh, Justin's off his rocker. This doesn't have a second degree. This is just a first degree. Same thing with this over here. But it turns out, in this form, it doesn't look like it. But we would actually have to use the FOIL method. We would have to distribute these within each other in order to get a quadratic, in order to get something with a degree of 2. So we're gonna cover FOIL. We're gonna review that a little bit. A really important topic. So we have first, outside, inside, last. So let's identify the firsts that we have. I'm kind of a visual learner myself. I'm going to be using red for the first part of FOIL. So F for first. The first one in the first set of parentheses is x. The first one in the second set of parentheses is also going to be an x. All right, so we've completed the F part of FOIL. Now we want to do the exact same thing for the O part. So O stands for outside. So if we look only at our first binomial, we can tell that the outer part of this is going to be x. And if we look at the second part, the outermost layer, if you will, the outermost layer on this side would have to be 2. So the O part of FOIL, outside, is comprised of this x and this 2. So then we have the I part of FOIL. I stands for inside. So what two things happen to be on the very inside, the very middle of this, the two I can't talk this evening. I apologize for that. So the inside is what we get when we multiply this 1 times this x. They're both kind of on the inside of things. X and 2 are on the outside, and then 1 and x are on the inside here. That brings us to our very last part of the FOIL. We have L, which stands for last. So the two things that appear last are going to be this 1 and this 2. So let's go ahead and see if we can turn this into a quadratic. So the red is F. F stands for first, which means we're going to do this first times this first. We're going to multiply x times x, and that would get us x to the second power, also known as x squared. And then we're going to move on to O. So on the outside of things, we have an x, we have a 2. Multiply those both together, we get 2x. So we're going to get a plus 2x. So we've done F, we've done O. We're going to move on to I, which is inside. So inside we have 1 times x. Those are the two things that are on the inside of this, so that would just get us plain old x. And then lastly, we have L, which stands for last, which means we're going to multiply this 1 by this 2. And then we can definitely simplify. We can combine a 2x and an x. We're going to get a nice, neat little 3x plus 2. I don't know about you, but my mind is blown right now. I am in awe over how this works, because it looks like we don't have anything that's remotely close to a quadratic. Remember, we said that this has a degree of 1, this has a degree of 1, so how is it even possible to get a quadratic? So when you multiply things like that together with different powers, you add the exponents together. So x times x, x to the first times x to the first, you always add the exponents together. 1 plus 1 is 2. That's where this x squared came from. We just added the invisible 1 exponents, and that's what we get for our new power. So these two, it doesn't look like it, but they are actually equivalent to one another. You might be wondering, why is it important? Why do we even care about changing the way things look like this? It doesn't really seem all that useful or important. And you might be right. I mean, at first it doesn't look like it, but as we progress more through this lesson, and as you progress more through your own mathematical journey, as if you will, you'll be able to see just how important this is in a wide variety of ways, in a wide variety of things you'll be able to use it for. So solving this is really hard, but solving this is really, really easy. What if we have just this on the right? What if we had x squared plus 3x plus 2? Let's say we have that equal to 0, and we want to find the x value that makes this true. So we have more advanced methods we can use to solve this efficiently, but that's not really what we're doing at the moment. We may have time to do this later in the video, but for now, we're going to save this for another time. Don't want to spoil the surprise. So these two are equivalent. So setting this equal to 0 and solving for it is really tricky. So why don't we just use this one instead? They're equal. Why not pick the easiest of the two if we know for sure that they're both equal to each other? We're always interested in finding the easiest, the fastest, the most efficient way of doing something. So we're going to take this thing that appears on the left, and we're going to solve this one instead of this thing we have on the right. So notice how we have a product of sums. That would be one thing times one thing, that's a product, and then of sum. So x plus 1 is a sum, x plus 2 is also a sum. So then what we have is, we already know that it's equivalent to this thing. We went from having, we have just a bunch of terms being added together. We have something plus something plus something. We've converted that into something times something, and it makes things much easier for us. So now let's see what we can do from here. So we want to set this equal to 0 and find the values of x that make it true. And remember, that's all solving really means. It means finding values of a variable that makes an equation true. So we're going to utilize that zero product property we had from before. The zero product property is the thing that says that if we have at least two things being multiplied and at least one of those things is 0, the whole thing is going to have a total value of 0. It's kind of like a domino effect. You knock over one domino, the whole thing topples. If just one little thing is equal to 0, the whole thing becomes 0. And that's the zero product property. Very exciting stuff. So let's suppose this entire binomial, this x plus 1, Let's see if we can make that equal 0. So that means we're going to take them separately. We have x plus 1 equals 0. And if we subtract 1 on both sides, in order to solve for x, we have to get rid of all the junk surrounding x. We're going to be left with just a simple x is -1. Perfect. So what does that tell us? It tells us that if we plug in a -1 right there for x, that means this whole thing is going to be 0. It's going to topple over the stack of dominoes that we've spent a long time neatly lining up, and it's going to turn the whole thing 0. So we found one of the two solutions. So a linear equation only has one solution. A quadratic could possibly have two, and that's one of the things that makes it particularly tricky. So we have our first one. We have our first solution. Now let's do the same exact thing for the second binomial. Do the same thing for the x plus 2. Set this equal to 0, and then solve for x. Subtracting a 2 on both sides gets us this. We're going to get x is equal to -2. Yay, we have our other solution. So this quadratic has two real solutions, and real solutions are opposites of imaginary solutions. And if you're not too sure about what imaginary numbers are, you will learn that more in depth when you take Algebra 2 and pre-calc. We're not really going to be getting into it so much in this lesson. Our goal is to focus on solving quadratics and then eventually graphing them. So we have our two solutions. We have -1, we have -2. What does that tell us? It tells us that if x is either of those two values, it doesn't matter which of these, but if x is either of these, the whole thing just becomes 0 because of that zero product property. So we've solved it. We've solved a quadratic. It doesn't even really seem like it was that big of a deal, but it helps us tremendously to know how to do things like this. We want to learn all of these advanced problem solving tools to help us a long way down the road when we take advanced math classes in the future. So like I said, this one is really hard to solve, but this one over to the left is much, much easier, much, much simpler to solve. So it's always in our best interest to not use this, but to use this instead. So we're going to spend some time discussing how to convert this x squared plus 3x plus 2, into something much, much easier and faster to solve. That is going to be one of the main ideas of today's lesson. Going from point A to point B. Very, very useful. So I'm actually going to keep this example. I really like it, and it'll help us make a connection that another problem probably couldn't help us to make, especially now we know what the solutions are. So let's work backwards. Let's say we're given point A. Let's say we're given x squared plus 3x plus 2. So how the heck do we go from this to that? They look nothing alike. I am so glad you asked. What we do now is we want to factor this. So we can see that we have two factors in the above equation on the left side of the equation. This would be one factor right here. This would be another factor. So remember that factors are just things that are being multiplied together. A number can have factors. So for example, 12 can have 6 and 2 as factors. It could have 3 and 4 as factors. It could have 1 in itself as factors. So variables in variable expressions and variable equations can also be factored in a very, very similar way to how numbers are. It's a bit more complex, but the general idea is really similar. So we have two factors. X plus 1 is one factor times x plus 2, which is the other factor. Our goal is to get it into this form. We want to factor this expression right here. So that's the goal of our current point in this class. We want to factor this, and eventually that will lead us to solve it. So we want to write this as a product of two different things. So we have one thing plus one thing plus one thing. We want to change it so that it looks something more like what we have up here. And it seems kind of convoluted at first. It may not seem like it makes that much sense, but I promise you it'll make more and more sense the more you practice, the more and more sense as you progress down your mathematical road of success. The more it'll become more apparent when you have more mathematical experience and you take more advanced math classes. So let's go ahead, and this seems really arbitrary, but we always want to start by adding up to our middle coefficient. So, and if you're not too familiar, if you're a little bit hazy on the concept of a coefficient, I urge you to go ahead and watch my video where I discuss a lot of vocab words. I think I put it out about a week ago on my YouTube channel, maybe 5-6 days. It discusses the difference between constants coefficients, and many other things. So if you're kind of hazy on coefficients, I highly recommend you go back and watch that video that deals with coefficients and other vocab words. So we want to add up to our middle coefficient, which is 3, and we want to multiply up to this number that's not a coefficient. This is a constant. It's a constant because it does not have a variable attached. If a number has a variable attached, it's a coefficient. If a number does not have a variable attached, if it's very, very lonely, that is a constant and not a coefficient. So our goal, at least in this class, is to find two numbers that add up to 3, which is our first coefficient, and then also multiply it to 2, which is the constant. Let's see what we can do. So we want to maybe start by listing the factors of 2. So we have 2 times 1, and then we also have -2 times -1, and that's it, I guess. Really anticlimactic, not very exciting. Only 2 things to choose from. So both of these would satisfy the multiplication requirement. It doesn't matter which of these 2 we pick, the multiplication is good to go. The problem is we have to find one that also satisfies this middle condition. We also have to find one that adds up to our middle coefficient, adds up to 3. So what I want to do is I want to take each of our factor pairs, and instead of multiplying them together, I'm going to add them together. So instead of 2 times 1, I'm going to convert it into 2 plus 1. And instead of -2 times -1, I'm going to turn it into -2 plus a -1. We get 2 plus 1 is 3. -2 plus -1 is -3. So we have 2 solutions. Now is the time when we decide which one we really want to use. So we want to add up to not a -3x, but a +3x. So it's going to have to be this top one. This one below it just does not work because we have a +3 and not a -3. So now that we have our 2 lucky numbers, being 2, being 1, this next step is going to seem kind of arbitrary as well. And I promise the more you do these, the more logical sense it will make. After a while, after some repetition, you'll get that light bulb moment thinking, oh, that's why we have to do that. So let's press on then, shall we? So we're going to take this x plus a number times x plus a number. And look, we're already really close to what we have in point B. We're almost there. So what do we have to do now? What we want to do is we want to plug in our lucky numbers into each of these spaces. So we have 2 and 1. I'm going to stick the 2 right there. I'm going to stick the 1 right there. So notice how we get exactly the thing we started with point B. We just did some factoring, which is the reverse of the FOIL method. So if we start with this and we do the FOIL method, we end up with A. But if we start with this and factor it, we end up with B. Factoring and the FOIL method are opposites of each other. They undo each other. They cancel each other out. So now we're not quite done yet. We have factored it, yes, but now we want to find the solutions. We want to utilize that zero product property that tells us that if this is 0, the whole thing becomes 0. And if this is 0, the whole thing is also going to become 0. So our question we want to ask ourselves would be, what values of x make this first thing 0? What value of x makes the second thing 0? So let's take it bit by bit. We have x plus 2. Set that equal to 0. And then if we subtract both sides by 2, we're going to get our first solution. That would be x is -2. So if x is -2, this whole thing becomes 0, making it a true statement. Algebra is the search for truth, and we've just found one of those truths. We want to do something similar for the other factor. Other factor is x plus 1. Let's solve it just like we solved the other one. So we're going to subtract a 1 on both sides, giving us a final solution of x is -1. So x is -2, x is -1. We have our 2 solutions. And that's it. That's how we use factoring to help us solve quadratics. It is a very, very notoriously tricky thing to learn when you're doing this for the first time. So don't worry, we're going to be doing many, many, many examples of factoring until I feel like we've all got it down. So I'm going to try a new one. Why is he writing so big? X squared plus 7x plus 10 equals 0. So just like before, we're interested in solving this. We're interested in finding the value of x that makes this a true statement. And we're going to do that with a little bit of factoring. So we want to factor this quadratic. I can't talk tonight, apparently. We want to factor this quadratic. X squared plus 7x plus 10 has a degree of 2. Therefore, it is a quadratic, and we want to factor that quadratic ultimately because it makes it much, much easier to solve. It is a shortcut. So to factor it, remember we want to add up to our middle coefficient. We want to find two numbers that add up to 7. We want to find two numbers that multiply to 10. So I'm not going to go through the tedious part of this. I'm just going to give you the answer. The two numbers that multiply to 10 and add up to 7 would have to be 5 and 2. Why, you might ask? Great question. 2 plus 5 is 7. 2 times 5 is 10. Wonderful. It's awesome. We've satisfied both of these requirements very easily. And remember what we did on that last problem a few minutes ago? We identified what I called our lucky numbers. In this case, our lucky numbers are going to be 2 and 5. So we're ready to just lay down the basic framework of what we expect this to look like. So we're going to do x plus our first number times x plus our second number. So then we're going to take x minus x plus 2. We're going to solve this for x. We're going to set it equal to 0, and then we're going to solve for x. X is negative 2. Let's do something similar for our other factor. Our other factor is x plus 5. We're interested in the value of x that makes this part also equal to 0. Accomplishing that by subtracting a 5 on both sides. So what do we have left over? Left over, we have x is negative 5. Perfect. We have our two solutions. That's it. It's not so bad. Very nice. So it's the zero product property that tells us if x is negative 2, this is 0. The whole thing has to be 0. It's going to obliterate our neatly stacked domino stack. It's going to topple everything over. And the same thing applies if we plug in a negative 5. So if we plug in a negative 5, this goes to 0. The whole thing actually goes to 0. So that's what it means by factoring. We just wrote it in terms of two factors, in terms of two things being multiplied together. So now let's talk about how to graph a quadratic. Actually, you know what? Maybe we should do a few more examples of factoring. I think that's a good idea. Let's say we have the following. We have x squared minus 11x plus 19 equals a negative 5. Exponent. I don't know why I wrote that so small. I might write it a little bit bigger this time. So before we can even get into the factoring, notice how there is a distinct difference between this one and the last few that we've done. The last few that we've done are equal to 0. They took some quadratic, set it equal to 0, and that's exactly what we have to do here. We can't solve it unless we can set this whole thing equal to 0. So we have to get rid of this pesky 5 and move it to the other side. Move it from the right side over to the left. We can do so by adding 5 on both sides. We get a 0 completely by itself over here. Very lonely. And then we have x squared minus 11x plus 19 plus 5, which happens to be 24, which happens to be plus 24, equals just 0. So let's find the solutions. Let's factor this thing. So we want to add up to negative 11, two numbers that add up to negative 11, and we want two numbers that multiply to make a positive 24. So multiples of 24, what are they? Well, because they add up to make a negative number, it means that they're going to both have to be negative, because a negative times a negative is a positive. A negative plus a negative is a negative. So we know it has to be two negative numbers that would work for us here. So 24 has negative 1 and negative 24. So if you add them together, it's not quite what we want. Yeah, sure, it satisfies the multiplication part, but it does not satisfy the addition part. We have to satisfy both of them in order to truly solve the quadratic. So we also have a -2 and a -12. If we combine those, we get -14. So that's not really going to help us all that much either. So let's try something else. Let's try a -3 and a -8. See what happens when we add these together. So -3 plus -8 is the same thing as -3 minus 8. We get -11. And look, that's exactly what we want to have. We want to have -11, and that's exactly what we have. So we're able to identify our lucky numbers now, with those being -3 and -8. So remember what we're going to do next. Remember what we did next after this step on the previous problem? We wrote the factored form without numbers. We wrote blank shells containing space that we will later fill with numbers. Set that equal to 0. And then we're going to enter our lucky number. So we have -3 would be our first one. That would be x plus -3, which is a fancy way of saying just x minus 3. And then we also have a -8. So we're going to do something similar. We could write it as x plus -8, but it makes things cleaner if we write it as x minus 8 instead. So let's find the solutions. So what does x have to be for the thing inside the box to be 0? If x is 3, the entire value of this box goes to 0. The whole thing becomes 0. We have our first solution. X has to be 3 for the first factor to be equal to 0. And then what else do we have? We have something similar. What does x have to be for this entire thing to be 0? It would have to be 8, because 8 minus 8 gets us that 0 we're looking for. Whoa, I didn't mean to erase that part. So we have these two things. We have a 3 and we have an 8. Perfect. We have our two solutions. That's how we factor quadratics. Let's try something else now. Let's try a bit more of a complex problem. Let's try 6x squared minus 18x minus 18 equals 6. So one thing that kind of jumped out at me right away would be the fact that our leading coefficient is a 6. And again, if you're not really too sure what leading coefficients are, if you're kind of hazy about that, I highly recommend you go back and check out the video I did that touches on algebra vocabulary. So if you go to my main YouTube channel, go to the playlists, you'll find that video underneath my algebra and pre-calc playlist. So go ahead and watch that if you're not too sure about what these words mean. So assuming that you watch those videos and assuming we're all good vocab-wise to this point, we can see that the leading coefficient is 6. And typically, whenever we have a situation like this, where coefficient A is 6, coefficient B we don't really care about, and then coefficient C is -18, in this kind of a situation, instead of just multiplying to C, we would actually have to multiply to A times C. So in the past, we had just, I can't remember what it was, we just multiplied two numbers, then multiplied to get this, and then added up to get our middle coefficient. So under normal circumstances, we would have to multiply A times C, find factors of AC that also add up to B, but not quite this time. We have to do something a little bit different. So we're always on the lookout. We're always on the prowl for ways to simplify something and make it a little bit easier to work with, a little bit faster, a little less tedious. So for example, I see that we have 4 terms. 3 of the terms are going to be to the left of the equal sign, and then we have one more over to the right of the equal sign. I see that all 4 terms contain a multiple of 6. So that being said, let's just divide everything by 6 to make it a little bit easier, much faster to work with. So if we divide everything here by 6, 6 divided by 6 is 1, leaving us with just x squared. 18x divided by 6, well, 18 divided by 6 is 3. So 18x divided by 6 is going to be 3x. And then this -18, when we divide -18 by 6, we get -3. And then we have over here, we have 6 divided by 6, which is just 1. So it's already looking a lot easier to work with, much simpler, much nicer, but there's still something we have to do before we can get into the factoring. Remember that we have to have it equal to 0. Can't be equal to 1. We have to move this 1 over to the other side by using a subtraction. That way, we definitely have a 0, which is exactly what we want. We need to have a 0 in order to factor this efficiently. So what we have left is the x squared is going to be unchanged. the 3x is going to be unchanged. In fact, the only thing that's going to change here would be this number we have trailing over at the end, this constant. The concept we started with, not concept, sorry. The constant we started with is a -3. So we're going to take that -3, we're going to decrease -3 by 1. We're going to do -3 plus -1, which is, in other words, saying that we have -3 minus 1, which would get us -4. So now that we're back to what we're used to. We see a leading coefficient of just 1. No longer 6 is just 1, which makes things tremendously easier for us. But we still want to do the same steps as before. We want to find two numbers that satisfy this requirement. They both have to add up to -3, but also satisfy the second requirement at the same time, the requirement that they must multiply together to make a product of -4. So let's think about ways to best find those two numbers. So let's make a list of the factors of -4. So for -4, we have -1 and +4. We also have +1 times -4. We also have 2 times -2, and that's it. We only have 3 whole number factor pairs that multiply to get us a -4. So our quest is to find which of these 3 also adds up to -3. We have to find the pair that not only multiplies to -4, but also adds up to a -3. And this is our quest. So let's take a look at all 3 of these pairs, starting at the bottom. What if we do 2 plus -2? 2 plus -2, that's the same as 2 minus 2, which is just a fancy way of saying 0. So the next one, we have 1, turn that multiplication into addition. We have 1 plus -4, which is -3. Same thing about this one right here up above. We have -1 plus 4, which is going to be a +3. So out of these 3 factor pairs, what do we want to use? It's going to have to be the middle one, because the middle one, it has not only the product of two numbers that make -4, but also the sum being -3, which is exactly what we want. So only this one satisfies both of those requirements. So our lucky numbers are 1 and -4. So we're going to do x plus a number times x plus a number equals 0. So we're going to do x plus our first number, x plus 1. And then we're going to do x plus our second number, x plus -4. What I want to do, instead of making this x plus -4, to clean things up a bit, I'm just going to call it x minus 4. So we've done the hard part. We factored, but we don't have the solutions quite yet. We want to utilize that zero product property that tells us that if one of those things is 0, the whole thing is automatically going to be 0. It's going to set off that domino chain reaction, topple everything over. So we want to take it factor by factor, just like we did in the previous examples. So I want to take this x plus 1 and figure out what values of x make this thing in particular equal to 0. Pretty easy to see. It's going to be x is -1. So we have our first solution. We have our first of 2 solutions. What do we want to do now? We want to do the same thing, except for our second factor. The first factor was x plus 1. We've already taken care of that one. Our second factor is x minus 4. We want to do the exact same thing to this one that we did in the last factor. We have x minus 4. And I'm sorry my handwriting is a bit bipolar. I'm going really small and then really big. Just bear with me, please. So we're going to set x minus 4 equal to 0. And then from there, it's pretty easy to see that x must be 4. Yay, we have both of our solutions. If x is 4, the whole thing becomes 0. If x is -1, the whole thing becomes 0. So these are the only 2 solutions to this quadratic expression. So that is how we factor. That's how we solve a quadratic by factoring. So let's see what other exciting things we have. I wonder if there's enough time to get into graphing. I think there might be. So let's go ahead and explore how to use that knowledge to help us graph. We're going to be graphing a quadratic. We know what quadratics are, but what the heck does the graph of a quadratic look like? We know what linear graphs look like. We know if we have something with a slope of 1, it's a flat line that does not increase, does not decrease. It has a slope of 0. If we have something with a slope, it's still going to be a line, but it's going to have a tilt to it. Now, this is a completely different ballpark, if that's even the right analogy to use. I might have butchered that one. But a quadratic looks kind of like a smile or a frown. That's always the way I've considered it to be. So a quadratic could look like that. The graph of a quadratic could look like either of these two things. So that's what it looks like when we graph a quadratic on the Cartesian plane. So let's discuss how to properly solve a quadratic, or how to maybe we solve it and then we graph it. How about that? So let's see what we have here. Let's say we have x squared plus 3x, and then we have minus 18. Set all of that equal to 0. Our goal is to graph this quadratic. So we know what the graph of a quadratic looks like. It's a smile or a frown, but specifically, where does it go on the graph? That's what we're trying to find out right now. But before we even do that, I want to let you guys know that the formal definition of I can't talk tonight. The formal name of the way a quadratic looks when you graph it is called a parabola. I want to just write that underneath. A parabola is just a bowl-shaped function. Whenever you have a smile or a frown when you graph a quadratic, those are both parabolas. So the graph of a quadratic will always be a parabola. So let's go ahead and see if we can solve this and then graph it. We have to solve it in order to graph it sometimes. In this case, we definitely do, but other cases we may not. Let's solve it by factoring. We want to add up to 3. We want to multiply to make a negative 18. I'm not going to bore you guys with the tedious busy work. I'm just going to get right into it. So it looks like the numbers that would work would be maybe a positive 6 and a negative 3. Let's test those out. Positive 6 times negative 3. Multiply them together, we get negative 18. Now let's do the same thing for addition instead. Let's do 6 plus negative 3. That gets us 3. And yay, it looks like it satisfies both of our requirements. Not only do the two numbers add up to make a 3, but the two numbers also multiply together to make a negative 18. It satisfies both of our requirements very nicely. So I think we're about ready to put this in factored form. We're going to do x plus a number times x plus another number and still keep it equal to 0. Our lucky numbers are going to be 6 and negative 3. So we have x plus 6, and then we have x plus negative 3, which is a fancy way of saying x minus 3. And the solutions are going to be x is negative 6. Because if x is negative 6, the whole thing becomes 0. The other solution is going to be x is positive 3. And just like with the last one, if x happens to be 3, this whole thing becomes 0, resulting in a true statement. So if x is any number besides negative 6 and 3, this would not equal 0. We would have a false statement. So there are only two x values that makes this true, and we've just found both of them. So let's figure out how to graph this thing. So these happen to be our x-intercepts. These two numbers, negative 6 and 3, they happen to be our x-intercepts. They happen to be the place where our parabola crosses the x-axis. So we want to plot both of them on the plane. I'm going to start with x is negative 6. Start at the origin, which is 0, 0. And for the negative numbers, we work our way to the left from the origin. So we have negative 1, negative 2, negative 3, negative 4, negative 5, and then lastly, negative 6 is what we're interested in. Same thing goes for the other solution we have, except this time it is a positive number and not a negative. So we're going to start at the origin and then work our way to the right. So we have 0 once again, and then that would be 1, 2, and then 3 would be right there, which happens to be the other number we're interested in. So let's maybe come up with some considerations of what this thing might look like. We know it's going to cross the axis here at 3. We know it'll cross the axis here at negative 6. So one way it might look would be, gosh, that was terrible. Let me try that again. Art skills leave a lot to be desired. Clearly, I flunked out of art school, and all I got was a t-shirt. So now we have this parabola. This is just one of many parabolas that go through those 2 points. What if we had something that's maybe a bit flatter that also goes through those 2 points? What if we have a smile instead of a frown? What was that? So there are infinitely many parabolas that go through these 2 points, but we have to narrow it down just to one parabola. There is just one parabola, and it is our mission now to find it. So let's determine if it's going to be a smile or a frown. So we can accomplish that by figuring out where it crosses the y-axis. Because if we figure that out, it will give us a really nice idea of what kind of parabola it'll be, whether it be a smile or a frown. So we can tell that at this point, x is equal to 0. So let's plug in x is 0 and see what happens. So we have x squared plus 3x minus 18 equals 0. All right. Next, what we want to do is just to plug in a -6 for both of these x's. So -6 times -6 is positive 36. -6 times positive 3 is -18. Or hang on, I got a bit ahead of myself there. We don't want to do that. We actually just want to plug in a 0 instead. So we're going to make this x into a 0. We're going to make this x into a 0. So 0 to the second power is still going to be a 0. 3 times 0, of course, is 0. -18, we do not change that at all. So we have -18 is equal to, whoops, we want that to actually be y. So we have this is equal to y. We have this one is equal to y. So as you guys can see, y is just going to be a number. Y is just going to be -18. So we're going to go down all the way down on the y-axis, starting at 0, starting at the origin. We're going to go all the way down to -18. So one consideration would be something like this, but how do we know where to stop? How do we know it's not going to be something like this? So what we want to do is we want to identify the axis of symmetry. And what that means is that we want to draw a line for which things will be symmetric. It'll be a mirror image on both sides of the line. But I want to use maybe a different color to make things a bit clearer. So with an axis of symmetry, things are going to be exactly the same on both sides. We treat it like a mirror. So for example, if we have something like this, if we had a downward facing parabola like that in an axis of symmetry, the axis of symmetry tells us absolutely that we're going to have basically a mirror image, the same exact function behavior occurring on the opposite side of the line. So that's the basics of what a line of symmetry is. And it's important to know how to find the line of symmetry because that will tell us whether we're going to end here or end there or anywhere really. We need that axis of symmetry to tell us how to draw what we're trying to draw. So we have when x is 0, y is -18, so we have a point right there. So the axis of symmetry is going to be exactly in between these 2 points. So if I wanted to make a number line right here, maybe a little bit better. So we have -6, we have a +3. So to find the axis of symmetry, we're interested in the number that falls exactly in between them. 0 obviously doesn't work because the distance between -6 and 0 is a 6. Distance between 0 and 3 is a 3. They're not the same, so obviously it can't be 0. So they have a total distance apart of 9, which means we want to cut 9 in half and have that be the midway point relative to whatever point we choose, be it left or right. So half of 9 is 4.5. So what I want to do is I want to subtract 4.5 from 3. I'm going to subtract 1, subtract 2, subtract 3, subtract 4, taking us to -1. And then I'm going to subtract 1 more, which takes us to -1.5, otherwise known as -3/2. So we found our axis of symmetry. We found out that the x value, x equals -3/2, has to be the location of the axis of symmetry. So -3/2 would be right here. So I'm going to make our axis of symmetry just like that. And then what? Well, then we want to figure out what happens when we plug our axis of symmetry into the original expression. What happens if we plug in -3/2 into our equation? So we have x is -3/2. I'm going to plug that into the quadratic and see what we get. Instead of x squared, we're going to have -3/2 squared. And then we're going to have plus 3 times negative 3/2. And then the negative 18 is going to be unchanged. So let's see what this evaluates to. So negative 3/2 to the second power is positive 9/4. And then we have the second term would be negative 9 over positive 2 minus 18. So to make any kind of sense of this whatsoever, we want to have a common denominator and then simplify. So we have 4 would be the LCM. 4 would be the LCM, the least common multiple between 1, which is our first denominator, 2, which is our second denominator, and then 4, which is our other denominator. So 4 is going to have to be the LCM, the least common multiple. So that means we're going to leave this first one alone. We don't have to do anything with 9/4. But this 9/2, we do want to put it over 4 somehow. So 9 over 2 is equivalent to some number over 4. That would be 18 over 4. And then we have this negative 18 over 1. So negative 18 times 4 is, well, what am I trying to say here? So if 9 times 8 is 72, that means 18 times 3 is also going to be 72. That's not quite right. Hang on. So 18 times 4 is 72. I'm pretty sure. 17 over 4 because 72 over 4 because if we do 18 plus 18, we get 36. If we do 36 plus 36, we do get 72. Perfect. So surprisingly, I did that right. So let's find the common denominator and then simplify the numerator. So we have a common denominator of 4. We're going to do 9 minus 8 minus 72. So we have 9 minus 18, which is a 9. Negative 9. Then negative 9 minus 72 is going to be negative 81. So we have negative 81 over 4, which is, I'm going to use a calculator for this. That gets us about 20 1/4. So let's figure out exactly what to do with that information. Oop, 20 1/4. So that would be way down here. It's going to be past negative 18. It would be right here below. So we're going to plot that point on the axis of symmetry. The point goes on the axis itself. So now we have a really, really nice idea of what this thing is supposed to look like. We know it goes through this point. We know it goes through this point. It also goes through this point. And then this is going to be the absolute low. It's going to only dive up from this point. Can't get any lower than that. Goes through this point, and then it also goes through this point as well. So there you have it. I hope your mind is blown just as much as mine was by this. This is some pretty exciting stuff. I'm looking forward to showing you guys how this can pertain to real life problems in science and medicine and engineering and that kind of thing. This kind of thing is never going to go away, so it's a really good idea to study it and practice and review until you're really, really confident and comfortable with this material, graphing and solving quadratics. So I'll see you in the next video. Bye.